Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Lowest common ancestor of a binary tree, Leetcode 236. In this problem, we are given a binary tree and we have to find the lowest common ancestor, LCA, of two given nodes in the tree. According to the definition of LCA, the lowest common ancestor is defined between two nodes P and Q as the lowest nodes in the tree T that has both nodes P and Q as descendants, where we allow a node to be a descendant of itself. Now, in terms of constraints, we are given that all the node values in the tree are unique and both P and Q exist in the tree and P is not equal to Q. Now, let's take some examples. For this given tree, suppose P is equal to 2 and Q is equal to 8. And we can see that node 2's ancestor is 6 and node 8's ancestor is also 6. So, node 6 is the only common ancestor and also the lowest common ancestor of both nodes 2 and 8. Now let's take P is equal to 0 and Q is equal to 5. And in terms of definition of lowest common ancestor is defined as the lowest node for which P and Q are descendants. And visually we can see that that node is node 2. Another way to say this is that ancestors of 0 are 2 and 6 and ancestors of node 5 are 4, 2 and 6. So the lowest common ancestor here is node 2 because it is at the deepest level when it comes to binary tree and is ancestor of both 0 and 5. Even though root node 6 is also a common ancestor, it is not the lowest one. So in this case we will return 2 as our answer. And now let's take example 3. Suppose P is equal to 2 and Q is equal to 4. Here node 4 is descendant of node 2 and according to the LCA definition, a node can be a descendant of itself. So node 2 is also a descendant of node 2. So that's why lowest common ancestor of both nodes 2 and 4 is 2. Now in terms of solution, one of the simplest approaches is to start from the root node. Since the root is always a common ancestor of every node in the tree, we start here. It is not necessarily the lowest common ancestor, but it is a common ancestor initially. Next, we find and store the paths for the nodes P and Q in a data structure like a list. For example, let's consider the given tree and P equal to 0 and Q equal to 5. Then path from root to P equal to 0 will be 6, 2 and 0. That is this path. And path from root to given node 5 will be 6, 2, 4 and 5. And this is this path. So now, once we have these paths, we can compare the paths element by element to find the last common node. So the first node we see is 6, which is common to both the lists. Then we see 2, this is also common in both the lists. Then the third element is 0 in list 1, but 4 in list 2. So this is where the paths diverge. So the last common ancestor before they diverge is 2, which is our lowest common ancestor. And to find the paths from root to the specific nodes P and Q, we will perform DFS on the tree until we locate those nodes. So in terms of time complexity, it will be O of n, where n is the number of nodes in the tree. Since in the worst case, we may need to traverse all the nodes to find P or Q. And in terms of space complexity, since we will be using recursion stack, it will be O of h, where h is the height of the tree. And in the worst case, in case of unbalanced binary tree, it will be equal to O of n. Now this is a good approach when it comes to time and space complexity. However, we can make the code cleaner and simpler. For example, we are traversing the tree twice to find nodes P and Q. Can we somehow do it in one go? Let's look at it with the example again. So again we start at the root node and we check if root is equal to P or Q, that is 0 or 5, and the answer is no. So we go deeper. We see node 2. We again check, is node 2 equal to 0 or 5? The answer is again no. So we go deeper. Then we see node 0. We again check, is node 0 equal to 0 or 5? And the answer this time is true and it matches P. So we return back P equal to 0 from this point because we found P in this path. So then we come back to node 2 and go to node 4. We again check, is it equal to 0 or 5? The answer is no. So we go deeper, we come to 3. And since node 3 also doesn't match 0 or 5 and it is a leaf node, we return null from this point because we couldn't find either P or Q in this path. Then we come to node 4 and go to node 5. And this time we again check if it matches 0 or 5 and it does match Q equal to 5. So we will return 5 from this point. Then we come back to node 4 and we get null from the left but a non-null value 5 from the right. So we will propagate 5 to the parent so as to tell that it found node 5 in this path. Now we come to node 2, and it is the first node which gets non-null values from both left and right. That is, it gets 0 from the left and 5 from the right. So when we get two non-null nodes from the left or right of it, that means we found both P and Q as a descendant to this node, and this node is a LCA. So we found the LCA and we return back 2 to the parent node. Similarly, our recursion continues on the right side as well. So we go to node 8, it doesn't matches P or Q. So we go down, we come to node 7, it also doesn't matches P or Q. And since it's a leaf node, we will return null from here. Then we go to node 9 and it also doesn't matches P or Q. And since it is also a leaf node, we will return null from here. And since node 8 gets null from both left and right, we will return null to node 6. And finally, once we are done with the recursion, we come back to node 6, and on the left side we will get 2 and on the right side we are getting a null. So at the root level we will return 2 and that will be our answer. So this is how we find the lowest common ancestor. Here is a cleaner picture of the example we just covered, illustrating the DFS to find the lowest common ancestor. If you are interested, please check out the link in the description below. Let's take one more example. Now let's take P equal to 2 and Q equal to 4. So again we start the recursion from root node 6 and check if it is equal to P equal to 2 or Q equal to 4, and the answer is no. So we go deeper. Then we come to 2 and check if it is equal to 2 or 4, and this time it is equal to P equal to 2. So we will return 2 from here. And note that since we return from this point itself, we will not find Q equal to 4 explicitly, but still our algorithm will work. I will explain it in a bit. We repeat the same process on the right side as well. We check if 8 is equal to 2 or 4, the answer is no. So we go deeper and come to node 7, and we again check if 7 is equal to 2 or 4, and the answer is again no. And since it's a leaf node, we will return null from here. Then we go to 9, and since it is a leaf node and it is not equal to either P or Q, so we will again return null from here. Now at node 8 we get null from both the sides, so we return null to the parent. And at the root node we get 2 on the left side but null on the right side, so we will return the non-null value, that is 2, which will be our LCA. And the reason this logic works is because suppose if 4 was somewhere on the right side, then we would have got 4 at the parent level, that is 6, and 6 would have been our LCA. But since 4 is descendant of 2 and it is guaranteed that both P and Q are present in the tree, so we can safely return the ancestor 2 from this point without explicitly checking its descendants. So to summarize our approach, we start the recursion at the root node, and if at any point in the recursion the current node is null, then we will return null. If the current node in the recursion is equal to either P or Q, then we will return the node itself. If we don't match any of the base cases, then we will recursively search the left and right subtrees for the nodes P and Q. And if both the left and right recursive calls return non-null values, it means current node is the LCA. So we will return current node. But if only one of the recursive calls returns a non-null value, we will propagate that non-null value upwards because it indicates a path where node P or Q is found. And in case node P or Q is descendant of other node, then we have found both the nodes. And the time complexity of this approach stays O of n, where n is the number of nodes in a tree, because in the worst case, we might traverse all the nodes. And in terms of space complexity, it will be O of h, where h is the height of the tree. And in the worst case scenario of a skewed tree, this can be O of n. Now let's jump into the code part. If current root is null, that is we found the empty subtree, or the root is equal to P or Q, meaning we have found one of the target nodes, then we will return the root. Then we recursively search for P and Q on the left side and the right side of the tree and store the results in variables left and right respectively. If both left and right are not null, that means we found P in one subtree and Q in another, then we will return the current root because the current node is their lowest common ancestor. But if only one of left or right is non-null, then we will return the non-null value. This indicates that either P or Q was found on one side of the subtree. If both are null, it means neither P nor Q was found in the subtree, so we will return null. Now let's submit this code. Cool. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up. and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.